Welcome to 5-Minute Papers on AI for the Planet. I'm Grace Lindsay. Our paper today is Samudra, an AI global ocean emulator for climate. Let's get started. The world's oceans, driven by wind, heat, salinity, and other forces, display rich and complex dynamics over many spatial and temporal scales. And these dynamics matter for human activities, whether it's managing fisheries or planning a ski season. So scientists need to be able to predict what the oceans are going to do in advance. To do so, they turn to numerical simulations. For example, the OM4 model, which is used as part of the global climate simulations that help us predict the impacts of climate change. These numerical simulation models use well-established equations to describe the many physical interactions that occur between different components of the ocean. But these simulations take a lot of time and compute power to run. Simulating a century's worth of ocean activity with OM4, for example, takes 8 days running on nearly 5,000 CPUs. And that's a problem because scientists want to be able to run these models multiple times. Doing so lets them understand uncertainty about the future by creating a distribution of possible predictions. It also makes it possible to explore different hypothetical futures, like when considering different paths that humans can take to try to slow climate change. To make ocean simulators easier to run, this paper builds an emulator. An emulator is simply a model that is trained to replace a more complex simulation. In this way, the emulator isn't meant to be a more accurate model of ocean dynamics, nor does it learn directly from the ocean data itself. Rather, this emulator is built to replicate what OM4 would do, but faster and using much less compute. To see how it can do this, let's first look at how the problem of training the emulator is framed. This equation shows us that the emulator model F needs to take in the state of the ocean phi at the current time, along with the state one time step in the past. It should then output or predict the state of the ocean at the next 2 time steps. These ocean states are highly simplified descriptions of relevant physical variables defined for each location on a grid. This includes temperature, salinity, surface height, and velocities. While OM4 describes these values separately for 75 different depths and updates them using 20-minute time steps, for their emulator, the authors reduced this to just 19 depths and time steps of 5 days. They also reduced the spatial resolution of the model. These choices all help the emulator to run faster. Importantly, we can't predict the state of the ocean in the future just by looking at the ocean in the past. Ocean dynamics are also driven by interactions with the atmosphere. So at each time step, the model also takes in the current atmospheric state, which is provided from historical data. To build a model that can do this, the authors use a U-Net architecture. This is an artificial neural network that takes an image-like data of a certain size, compresses it through a bottleneck, and then expands it back out, using cross connections from the encoder side of the model to the decoder to make sure that fine-grained spatial information is not lost. Here, the input is the current and past ocean state and atmospheric conditions represented on a map, and the output is a map of future ocean states, which then gets compared to the correct values from OM4 during training. This training is done using OM4 values and atmospheric data from the years 1975 to 2014. This model, which the authors call Samudra, has 135 million parameters, but its simple computational form means it can be run quickly. A year of ocean dynamics takes about 90 seconds to run on a single GPU, which is 75 times faster than OM4. To determine if a Samudra is a good stand-in for OM4, the authors initialized Samudra with ocean states from September 2014 and then let it run in autoregressive mode by repeatedly feeding its own output back in as input for 8 simulated years. Shown here are the temperature trends over this test period for 3 different ocean depths, as predicted by OM4, compared to 2 versions of Samudra, one that uses all ocean variables and one that doesn't include velocities. In general, Samudra is able to replicate OM4's behavior, though there are some discrepancies. Looking specifically at the El Niño Southern Oscillation, which is a major driver of weather patterns across the globe, both emulators are able to capture the general dynamics. While these emulators appear to work on short timescales, their long-term behavior is harder to predict. Small errors in an emulator at one point in time can accumulate and lead to nonsensical results in the long run. To test for this issue, the authors ran a 100-year-long simulation on Samudra. To provide the atmospheric data for this, they simply took a 10-year period from the past and repeated it over and over. As can be seen here with the El Niño metric, the emulators remain stable even over a century-long simulation. Another concern with emulators is that they may become too tailored to the patterns that they were trained on, and this issue may be at play in Samudra. Specifically, the authors note that Samudra has trouble capturing the warming trend that happens over its 8-year test run. Interestingly, the authors' attempts to fix this issue resulted in models that became unstable in long-term simulations. The extent to which this trade-off in performance represents a fundamental challenge for emulators remains to be seen. That's all for this episode. Remember to subscribe to this channel for more examples of how AI can be used to predict and protect our planet.